Right now, photons are reaching Earth that should not exist, not in theory, not in some distant future correction of physics. Right now, light, actual, measurable light, is being detected by the most advanced telescope humanity has ever built, carrying information from objects that, according to everything we thought we understood about the universe, should not have had time to form. Not slowly, not gradually, fully formed. Galaxies, massive ones, shining through a universe that, at that moment in time, was supposed to be almost completely dark. And here is the part that should make you pause. This is not a glitch. It is not noise. It is not a misreading buried in uncertainty. It has already been confirmed. Something out there is older than it should be, brighter than it should be, more structured than it should be, and you are about to see why some scientists quietly started asking a question they rarely say out loud. What if the beginning of the universe didn't happen the way we think it did? Because if this light is real, and it is, then something about the earliest moments of existence is missing from the story. And once you see where that leads, you won't look at the universe the same way again. Take a breath. We are going back to the moment when the first light was supposed to exist, and then we are going to step beyond it. You are going to see what the James Webb Space Telescope actually detected, why those detections immediately triggered alarm across the cosmology community, how galaxies appeared far too early, far too massive, and far too bright, and why some of them seem to have formed when the universe was only a few 100 million years old. You are going to understand what that light physically is, how it traveled for over 13 billion years to reach us, and why its existence challenges one of the most stable models in modern science. You are going to hear what scientists said behind closed doors when the first data came in, and you are going to see what happens next if these observations continue to hold. If this sounds like the kind of thing that keeps you awake at night, the kind of question that doesn't let go once it gets into your head, hit subscribe, because this is not just a discovery, it is a crack in the timeline of the universe itself. And the deeper you go into it, the less stable everything starts to feel. For most of human history, the early universe was a blank page, not metaphorically, literally. We could not see it. Every telescope ever built before a certain point had a limit, a wall. Look far enough away, and you are looking back in time. That part is simple. Light takes time to travel, so distant objects appear as they were millions or billions of years ago. But eventually, you reach a point where there is nothing to see, not because there is nothing there, but because the universe itself was not ready to be seen. This period is called the Cosmic Dark Ages, and it is exactly what it sounds like. After the Big Bang, the universe was hot, dense, and opaque. Light could not travel freely. It scattered constantly, like headlights in thick fog. Then, about 380,000 years later, things cooled down enough for atoms to form. Light was finally able to move without being trapped. That light is still here today. We call it the cosmic microwave background. It is the oldest light we have ever seen. But after that moment, something strange happens. The universe goes dark again. Not completely dark, but empty. No stars, no galaxy, no structure. Just hydrogen gas, slowly cooling, slowly collapsing, waiting for hundreds of millions of years. Think of it like a city before it is built. The land is there, the materials are there, but nothing has been assembled yet. No buildings, no lights, no movement, just potential. That is what the universe was like, and according to everything we understood, it should have stayed that way for a long time. The first stars were expected to form gradually, small at first, then larger, then clusters, then galaxies, step by step, slowly, predictably, but that assumption was one of the most consequential mistakes in modern cosmology. The model seemed solid. It wasn't guesswork. It was built from decades of observation, simulation, and mathematics that had survived constant testing. The early universe, according to this model, should have followed a very specific timeline. First, tiny fluctuations in density, almost nothing. Slight differences in how matter was distributed after the Big Bang. Then gravity begins to work. Over millions of years, those tiny differences pull more matter in. Regions get denser. Gas clouds collapse. The first stars ignite. Not massive ones. Not yet. Small, primitive, short-lived. These first stars, what scientists call population 3 stars, were supposed to be the seeds. They would live fast, burn hot, explode, and enrich the universe with heavier elements. Only after that process repeated, over and over again, would larger structures begin to form. Galaxy, but even those galaxies at first should have been faint. Irregular, barely holding together. Think of it like building a city. You don't start with skyscrapers. You start with tents, then small houses, then roads, then infrastructure. Only after generations of construction do you get something complex. That was the expectation, and the timeline for this process wasn't vague. It was precise. By about 400 million years after the Big Bang, the first small galaxies begin to appear. By 700 million years, things start to organize. By 1 billion years, you begin to see recognizable structures. That is the story the universe was supposed to tell. Slow growth, layer by layer, cause and effect. Nothing rushed, nothing skipped, and for a long time, every observation we had seemed to support that, until we built something capable of looking deeper, much deeper. The James Webb Space Telescope was not designed as just another telescope. It was designed as a time machine, positioned nearly 1 million miles from Earth, at a point in space where gravity balances in a delicate equilibrium. It sits in permanent darkness, shielded from heat, staring outward into the deepest parts of the universe. It does not see like your eyes. It does not even see like older telescopes. It sees infrared light, light that has been stretched, because as the universe expands, light traveling through it gets stretched along with space itself. Wavelengths grow longer. Visible light becomes infrared, so the further away something is, the older it is, and the redder it appears. This is called redshift, and it is one of the most powerful tools we have, because it lets us measure time, not directly, but precisely enough. When Webb looks at a galaxy with a redshift of, say, 10, it is seeing something that existed when the universe was less than 500 million years old. That is not interpretation. That is measurement. So when Webb began its deep field observations staring at tiny, seemingly empty patches of sky for hours, collecting faint photons that had traveled for over 13 billion years, scientists expected to see exactly what the model predicted. Faint, small, primitive galaxies. The earliest building blocks. What they saw instead should not have been there. At first, it looked like noise, blurry smudges, points of light, nothing unusual. But then the data came in, and the redshift measurements started to stabilize. Objects at redshift 10, then 11, then 12. That alone was not the problem. We expected to find early galaxies. That was the entire point. The problem was what those galaxies looked like. They weren't small. They weren't faint. They weren't primitive. They were massive, bright, structured. Some of them appeared to contain hundreds of millions or even billions of stars, and they existed at a time when the universe should not have been old enough to build them. Not even close. Think of it like walking into a forest expecting to find saplings, and instead finding fully grown trees. Not just a few, an entire landscape. That is what Webb saw. Galaxies that looked like they had already lived long lives, in a universe that had barely begun. At this point, the reaction was cautious, because science has a rule. If something looks impossible, assume you are wrong first. Maybe the redshift measurements were off. Maybe the light was being distorted. Maybe something along the line of sight was tricking the instruments. Gravitational lensing, for example, can magnify distant objects, making them appear brighter, and larger than they really are. Think of it like looking through a warped piece of glass. Things behind it can look bigger than they actually are. So that was the first explanation. Maybe these galaxies weren't really that massive. Maybe they were being amplified. But when scientists began checking for lensing effects, the data didn't support it. These objects weren't being magnified enough to explain what we were seeing, which meant something else had to be happening. And this is where the tension began. Because if the measurements were correct, then the timeline was wrong. The timeline was not just slightly off. It was being broken, quietly at first. In papers, in internal discussions, in cautious phrasing that tried not to overstep what the data could actually support. But the implication was sitting there, impossible to ignore. If galaxies this massive existed this early, then something in the process of structure formation was happening faster than our models allowed. Not a little faster, orders of magnitude faster. And that creates a problem. Because the early universe is one of the most tightly constrained parts of cosmology. The physics that governs it, gravity, dark matter behavior, gas cooling, star formation rates, has been tested against observations across multiple independent lines of evidence. You don't change it casually. You don't say, maybe it's different, without consequences. Because if it is different, then everything that builds on top of it changes too. Think of it like a foundation. If you discover that the ground beneath a building is not as stable as you thought, you don't just patch one wall. You have to reconsider the entire structure. And the early universe is the foundation. So when Webb started returning these observations, scientists did not immediately jump to conclusions. They tried to find ways to fit the data into the existing model. Maybe star formation was more efficient than we thought. Maybe early gas clouds collapsed faster. Maybe the first stars were much more massive, producing light more quickly. Each of these ideas was explored. Simulations were adjusted. Parameters were pushed to their limits. But even when you stretched the model as far as it could reasonably go, it still struggled. The galaxies Webb was seeing weren't just early, they were mature. That is the key detail. They showed signs of structure, organization, even chemical enrichment in some cases, meaning multiple generations of stars had already lived and died. And that takes time, a lot of time. Time the universe did not appear to have. Now, to understand why this is so unsettling, you have to understand what that light actually is. Because we keep saying light, but that word hides the real weight of what's being detected. This is not just brightness, this is information. Every photon arriving at Webb's detectors carries a history. It carries data about where it came from, what it passed through, and how long it has been traveling. When a telescope like Webb observes a distant galaxy, it is not just taking a picture, it is reading a signal that has been traveling across space for billions of years. Think of it like receiving a message in a bottle, except the bottle was thrown into an ocean 13 billion years ago, and it finally washes up at your feet today. The message inside tells you what the world looked like when it was sent. But here's the problem. Some of the messages Webb is receiving describe a world that should not have existed yet. That is the tension. Not that we are seeing far, but that what we are seeing far away does not match when we are seeing it. Light from these galaxies left them when the universe was still in its infancy. And yet, what that light shows is something far more developed. It's like opening a photograph labeled Earth 10,000 BC and seeing skyscrapers. You would not assume the photograph is correct. You would assume something is wrong. But Webb keeps finding more of them, more candidates, more galaxies at extreme redshifts that look too big, too bright, too evolved. And each new observation adds weight to the same question. At what point does a pattern stop being an anomaly and start being a signal? This is where things begin to split, because not all scientists agree on what this means. Some argue that the data is still too early, that initial measurements often get refined, that redshifts can be misinterpreted, that follow-up spectroscopy, the more precise way of measuring distances, might bring these galaxies back into alignment with expectations. And that is a valid position. Science moves carefully for a reason. Extraordinary claims require extraordinary evidence, but others are less comfortable dismissing it. Because even if some of these objects turn out to be less extreme than they first appear, not all of them will, and it only takes a few confirmed cases to create a real problem. A confirmed galaxy with too much mass, too early, is enough, because it forces you to explain how it got there. And right now, that explanation is not clear. Some researchers have proposed that we are underestimating how quickly matter can collapse in the early universe. That dark matter halos the invisible scaffolding that galaxies form around may have assembled faster than expected. Think of dark matter like the frame of a building. You don't see it directly, but it determines where everything else goes. If those frames formed earlier, then galaxies could form earlier too. That is one possibility. Another idea is that the first stars were fundamentally different. Much larger, much hotter, capable of producing enormous amounts of light in a short time. If that's true, then these galaxies might not be as massive as they appear. They might just be unusually bright. But even that has limits. Brightness alone cannot account for the structure we are seeing. And structure requires time, which brings us back to the same unresolved tension. Something is happening earlier than it should, and we don't yet know what. But the moment that realization truly landed was not when the first images were released. It happened in quieter places, in data rooms, in late-night analysis sessions, when individual researchers started comparing numbers, cross-checking models, running simulations that refused to match what Webb was showing. That is when the question stopped being theoretical and started becoming real. It happened slowly, not as a single announcement, not as a headline, more like a shift in tone. At first, the language in papers was careful. Words like candidate, potential, requires further confirmation. The usual caution that surrounds anything at the edge of measurement. But beneath that language, something else was building, because the detections kept coming. Different teams, different methods, same pattern. Galaxies at redshifts greater than 10, some pushing toward 13, even tentative candidates beyond that. Each one a data point, each one a pressure on the model. And then came the moment where it stopped being easy to explain away. Spectroscopic confirmations. Not all of them, not the most extreme cases, but enough to say, with confidence, that at least some of these objects were exactly as distant, and therefore as early as they appeared. That matters, because photometric redshift, the initial method used to estimate distance, can be uncertain. It relies on measuring how light is distributed across different wavelengths and fitting it to expected patterns. It's powerful, but it's not definitive. Spectroscopy is different. It looks for specific signatures, fingerprints in the light, that correspond to known atomic transitions. When you see those lines shifted to certain wavelengths, you can measure distance with far greater precision. So when those confirmations started to come in, the room got quieter, because now it wasn't just a possibility. It was real. At least some galaxies were already in place, already shining, when the universe was only a few 100 million years old, and they were not what we expected. Now, here's where the story becomes more subtle, because it's tempting to think of this as a single contradiction, as if the universe is simply wrong. But that's not how it works. The universe is not wrong. Our model is incomplete, and that difference matters, because it means we're not looking at an error, we're looking at a clue. Think of it like solving a puzzle. If one piece doesn't fit, you don't throw out the entire picture. You look for what you're missing. But if multiple pieces start refusing to fit in the same region, you begin to suspect the picture itself needs to be redrawn. That is where we are now, because the early universe is not just about galaxies. It's about something deeper, the process called Reionization. This is one of the key milestones in cosmic history. After the Dark Ages, when the first stars and galaxies formed, they began emitting high-energy radiation. That radiation interacted with the surrounding hydrogen gas, stripping electrons from atoms and making the universe transparent again. This process reionization marks the transition from a dark, opaque universe to one filled with light. And it has a timeline. According to existing models, reionization should have taken place gradually between about 400 million and 1 billion years after the Big Bang, driven by the first generations of stars and galaxies. But if galaxies are forming earlier, and in greater numbers, and with higher luminosity, then reionization might have happened differently, faster, more unevenly, or driven by sources we didn't account for. That might sound like a small adjustment, but it's not, because reionization affects everything that comes after. It changes how light travels, how structures form, how matter interacts. It's like changing the climate of a planet during its earliest development. Everything downstream shifts, and Webb's observations are starting to suggest that the early universe may not have been as slow and uniform as we thought. It may have been chaotic, bursty, regions lighting up earlier than expected, others lagging behind, a patchwork of formation rather than a smooth progression. Now imagine trying to reconstruct history under those conditions. It's like trying to understand how a forest grew. When some areas suddenly exploded with growth, while others stayed dormant, the patterns become harder to read. The timeline becomes less clean, and that brings us to a deeper question. What if the problem is not just how fast galaxies formed, but what they formed from? Because all of this depends on the behavior of dark matter. Dark matter is the invisible framework of the universe. It makes up most of the mass. It does not emit light. It does not interact with electromagnetic radiation, but it exerts gravity, and it shapes how matter clumps together. Without dark matter, galaxies as we know them could not exist. They would not have enough gravitational pull to hold themselves together. So the standard model assumes a specific type of dark matter, cold dark matter, slow-moving, clumping efficiently, building structures over time. But if galaxies are forming earlier than expected, it raises the possibility that dark matter might not behave exactly the way we think it does. Maybe it clumps faster. Maybe it interacts in ways we haven't accounted for. Maybe there are additional forces or particles involved. These are not conclusions. They are possibilities, but they are being taken seriously. Because when observations and theory start to diverge, you follow the divergence. And this is where the scientific community begins to split into camps, not in conflict, but in interpretation. Some researchers argue that the discrepancy can still be resolved within the existing framework, that we are underestimating certain processes, that better data will bring things back into alignment. Others are less certain. They see these observations as the beginning of something larger, a sign that our understanding of the early universe may need revision. Not a complete overhaul, but a shift, a raffinement, or something more. And here's the part that makes this story different from most. We are not looking at a mystery from the distant past. We are watching it unfold in real time. Right now, new data is being collected. Right now, new observations are being analyzed. Right now, the picture is still changing. And that means the answer does not exist yet. That uncertainty is not a weakness. It's the signal, because there is a moment in every major scientific shift where the data arrives before the explanation, where reality shows you something clearly, but your framework for understanding it lags behind. That is the moment we are in, and you can feel it in the way scientists talk about this. Not publicly, not in simplified summaries, but in the details, in the phrasing, in the careful way conclusions are avoided, even when patterns are obvious, because everyone in the field understands the same thing. If this holds, it changes more than just a timeline. It changes how structure emerges in the universe. And that brings us back to the light itself, because we keep talking about galaxies being too big or too early, but that still doesn't fully capture what Webb is actually detecting. What it sees is not the galaxy directly, it sees its light, and that light is doing something very specific. It has been traveling for over 13 billion years across expanding space, through regions that no longer even exist in the same way. And by the time it reaches us, it has changed, stretched, shifted into infrared wavelengths that Webb is designed to detect. So when Webb looks at one of these early galaxies, it is not seeing it as it is seeing it as it was, at the exact moment that light left it. Think of it like looking into a mirror that reflects the past, not seconds ago, not minutes, but billions of years. You are not observing an object, you are observing a moment, frozen in transit. And that moment tells you something about how much had already happened by then. If the light shows a structured galaxy, then that structure existed at that time. If the light shows chemical complexity, then multiple generations of stars had already formed and died. If the light shows brightness at a certain level, then enough mass had already collapsed to produce it. Each photon is a piece of evidence, and when you collect enough of them, you get a picture. And right now, that picture is not matching expectations. Now, let's anchor the scale, because it's easy to lose it. When we say 13 billion years, that number stops meaning anything. So bring it closer. The Earth formed about 4.5 billion years ago. The dinosaurs went extinct 66 million years ago. Modern humans have existed for roughly 300,000 years. The light Webb is detecting left its source when the universe was younger than 500 million years old, before galaxies were supposed to exist in any meaningful form, before the processes we rely on to build structure had enough time to operate. That light has been traveling since before the Earth existed, before the Sun formed, before our entire solar system was even a possibility. And it arrives now, telling us something was already there. That is the scale of the problem, and it is also the scale of the opportunity, because if something formed earlier, then something caused it. And that cause is what scientists are now trying to understand. Some of the proposed explanations are subtle, adjustments to efficiency, to cooling rates, to how quickly gas can collapse under gravity. Others are more radical, suggestions that our understanding of initial conditions, the state of the universe just after the Big Bang, might be incomplete. That perhaps the density fluctuations were larger in certain regions. That maybe there were seeds for structure that we haven't accounted for. There are even discussions, carefully framed, about whether alternative cosmological models might need to be considered, not as replacements, but as tests, because that's how science works. You don't abandon a model because of one anomaly, but you also don't ignore repeated signals. You investigate, you push, you see where it breaks. And right now, there are stress points, but here's where it gets more interesting, because not all of the early objects Webb is detecting are the same. Some appear to be galaxies, others might be something else entirely. Compact source, unusual spectra, objects that don't fit neatly into existing categories. And this opens another possibility. What if we are not just seeing galaxies earlier, but seeing different kinds of objects that existed in the early universe and don't have direct equivalents today? Think of it like looking at Earth during a different era. The organisms you would see would not all resemble what exists now. Some would be transitional, some would be experimental forms of structure. The early universe might have had its own versions of that, objects that formed under conditions that no longer exist, objects that evolved quickly, disappeared, or transformed into the galaxies we recognize. If that's the case, then Webb isn't just showing us early galaxies. It's showing us a phase of the universe we've never directly observed before, a phase that was always theoretical, until now. And that makes interpretation even more complex, because you're not just comparing observations to a model, you're trying to classify something you've never seen. And that means mistakes are possible, misidentifications, overestimations, underestimations. All of that is part of the process. But even accounting for that, the signal remains. Something is happening earlier than expected, and the more we look, the more consistent that signal becomes. Which brings us to the people behind this, because science is not just data, it's interpretation, and interpretation depends on perspective. Some researchers have been cautious to the point of skepticism. They point out that early JWST data is still being refined, that selection effects biases in what we're able to detect might be making certain objects appear more common than they are, that we might be seeing the brightest, most extreme examples simply because those are the easiest to detect. Like shining a flashlight into a dark forest. You don't see everything. You see the things that reflect light back at you, and those might not be representative. That is a valid concern. But others argue that even accounting for that, the existence of these objects still requires explanation, because rarity does not eliminate reality. Even one confirmed galaxy that is too massive, too early, is enough, and right now we have more than one. We have a growing list, and each one adds weight, quietly, relentlessly, until eventually the question becomes unavoidable. Not whether something is wrong, but where. Where exactly does the model start to fail? That is the question no one can answer cleanly yet, because the model itself is layered. It's not one idea. It's a stack of assumptions, each one built on the one before it. Change one layer, and everything above it shifts. So scientists don't ask, is the model wrong? They ask, which part of it is incomplete? And to answer that, you have to go back even further, back to the very beginning. Not just the formation of galaxies, but the conditions that made galaxy formation possible in the first place. Right after the Big Bang, the universe wasn't uniform. It couldn't have been. If it were perfectly smooth, nothing would ever form. Matter would spread evenly, with no regions dense enough to collapse under gravity. But it wasn't smooth. There were tiny fluctuations, differences in density so small they were almost invisible. We know they existed because we can still see their imprint today in the cosmic microwave background. Temperature variations on the order of 1 part in 100,000. That is almost nothing, but it was enough. Those tiny differences became the seeds. Over time, gravity amplified them. Denser regions pulled in more matter. Less dense regions lost it. Structure emerged. Slowly, predictably, that's the foundation. Now here's where things get interesting. What if those initial fluctuations weren't as small as we thought? Or not as uniform? Or not distributed the way our models assume? Because if the seeds were slightly larger in certain regions, then structure could form faster there, much faster. Think of it like planting seeds in soil. If all the seeds are identical, growth is consistent. But if some seeds are already slightly larger or placed in richer soil, they grow faster. They dominate the landscape early. That could be happening on a cosmic scale. Localized regions of early structure formation, pockets of accelerated growth. And if Webb happens to be looking at one of those regions, it might give the impression that the entire universe formed structures early, when in reality, we're seeing an outlier. That's one possibility. But it raises another question. How likely is that? Because Webb isn't just seeing one object. It's seeing multiple, across different regions of the sky. And while selection bias could play a role, it becomes harder to explain everything as coincidence, which leads to another layer. Dark matter. We talked about it as the scaffolding of the universe, but what if that scaffolding behaved differently at early times? In standard models, dark matter is cold and collisionless. It moves slowly. It clumps under gravity, but it doesn't interact with itself in any significant way beyond that. But there are alternative ideas. Warm dark matter, self-interacting dark matter, exotic particle candidates that change how structure forms. If dark matter could collapse faster, or interact in ways that enhance clumping, then galaxies could assemble earlier. Not because the visible matter changed, but because the framework it sits on did. Think of building a city again. If the scaffolding goes up faster, the buildings follow. But changing dark matter is not a small adjustment. It's fundamental. It touches everything, from galaxy rotation curves to large-scale structure to gravitational lensing. So any modification has to be consistent with all of those observations. That's the challenge. You can't fix one problem by creating 10 more. Which is why most scientists are still trying to stay within the existing framework, pushing it to its limits before considering deeper changes. But the limits are being tested, and that's where tension becomes productive. Because tension forces clarity, it forces better data, better measurements, better understanding. And right now, one of the most important things happening is follow-up, because initial detections are just the beginning. Every candidate galaxy needs to be confirmed, its distance measured precisely, its mass estimated more accurately, its spectrum analyzed in detail. This is slow work, careful work, the kind that doesn't make headlines, but it's where the truth emerges. And as that work continues, some candidates are being revised. Some turn out to be closer than initially thought, some less massive, some less extreme. That's expected, but others remain, and those are the ones that matter, because they survive scrutiny, they resist explanation, they stay where they are in the data, and those are the objects that shape the conversation. Now imagine what happens if more of those survive, if the list grows, if the pattern strengthens. At some point, it stops being a question of interpretation and becomes a requirement for explanation. And that is where this is heading, because Webb is not done. It has barely begun. Every deep field it observes adds more data. Every survey expands the sample. Every spectrum sharpens the picture. And the next phase of this story is not about what we've already seen, it's about what we're about to confirm, because confirmation changes everything. It turns possibilities into constraints, and constraints force theory to adapt. And that adaptation is already beginning, not in a dramatic, headline-grabbing way, but quietly, in updated simulations, in revised parameters, in conversations that start with, "What if we adjust this?" and end with models that look slightly different than they did a year ago, because that's how science moves, not by sudden collapse, but by pressure, steady, accumulating pressure from observations that refuse to fit neatly into the existing framework. And right now, the pressure is coming from one place, the earliest light. Now, there is something important you need to understand about how fragile this part of cosmology is. The early universe is not something we can experiment on. We can't recreate it. We can't test it directly. Everything we know about it comes from light that has traveled across billions of years to reach us. That means we are always working with incomplete information, snapshots, fragments, clues, and we build models that best explain those clues. But those models are only as strong as the data supporting them, and when new data arrives, the model has to adjust, or it breaks. This is one of those moments, because the James Webb Space Telescope is not just improving our view of the early universe, it is expanding it. Before Webb, we had glimpses, hints, a few extremely distant galaxies detected by Hubble and ground-based telescopes, but they were faint, at the edge of detection, difficult to study in detail. Webb changes that. It doesn't just detect these objects, it resolves them, it analyzes their light, it reveals their structure, and that difference is everything. Because now we're not just asking, are there galaxies this early? We're asking, what are they like? And the answer so far is not what we expected. Some of these galaxies appear surprisingly compact, denser, packed with stars in a relatively small volume. Others show signs of rapid star formation, rates that would require enormous amounts of gas collapsing quickly. Some even hint at the presence of heavy elements, which means previous generations of stars had already existed. And that brings us back to time, because everything comes back to time. To build a galaxy, you need gas to collapse, stars to form, stars to evolve, stars to explode, elements to disperse, new stars to form from that enriched material. And all of that takes time, even under the most efficient conditions. Even with aggressive assumptions, there are limits, physical limits, and some of these galaxies appear to be pushing right up against those limits, or beyond them. Now, let's ground this again, because it's easy to let the abstraction take over. Imagine you're watching a video of a building being constructed. You know how long it takes. You've seen it before. Foundation, frame, walls, systems, finishing. Now imagine skipping to a timestamp where only the foundation should exist and seeing a finished skyscraper, not partially built, not under construction, finished. You would not assume the construction was just faster. You would question the timeline itself. That is what Webb is doing to cosmology. It is showing us structures that appear too complete for their moment in time, and that forces a deeper question. What if the early universe had access to processes we don't fully understand yet? Processes that accelerated structure formation, that bypassed steps, that allowed matter to organize more quickly. This is where some of the more speculative ideas begin to emerge, not as conclusions, but as possibilities being explored. One idea involves the role of black holes. Supermassive black holes exist at the centers of most galaxies. We know that, but how they formed so quickly is already a puzzle. Now imagine if, in the early universe, black holes formed even earlier, acting as gravitational anchors, pulling in matter rapidly, triggering accelerated galaxy formation around them. Think of it like dropping a heavy object into water. The water doesn't just sit still, it rushes toward it. If early black holes existed in greater numbers, or formed faster, they could have acted as seeds for rapid structure formation. Another idea involves variations in fundamental physics, not violations. Variation, slight differences in how forces behaved under the extreme conditions of the early universe. Changes in cooling rates, in particle interaction, in the efficiency of star formation. These are subtle shifts, but over cosmic time, subtle differences can produce large effects. Then there are ideas that push further, concepts like early dark energy, a temporary phase where the expansion rate of the universe behaved differently, allowing structures to form earlier before settling into the expansion pattern we observe today. These ideas are still being tested, still being debated, because each one has consequences. You can't introduce a new mechanism without affecting everything else, and the universe is consistent. That's one of its defining features. The same physics that explains the early universe must also explain what we see today, so any solution has to fit both. That's the challenge, and that's why this is not resolved yet, because every proposed explanation solves one part of the puzzle, but creates new questions somewhere else. And this is where the human side of science becomes visible, because behind every model is a person trying to make sense of it. Some are excited. They see this as an opportunity, a chance to refine our understanding, to discover something new. Others are cautious. They've seen anomalies before, signals that looked significant at first, but faded with better data. They want confirmation, more observations, more certainty, and both perspectives are necessary, because without excitement, you don't explore, and without caution, you get it wrong. Right now, both are present, and they're shaping how this story unfolds. And the next phase of this story is not theoretical, it's observational, because everything we've talked about so far, every anomaly, every tension, every possibility, depends on one thing: confirmation. Not more candidates, not more hints, confirmed measurements, precise distances, verified properties. Because once you confirm something, you can't ignore it, and that is exactly what scientists are working on right now. Follow-up spectroscopy, deeper observations, longer exposure times, each one designed to answer a simple question: is this real? And if it is, what exactly are we looking at? Because there is still room for revision. Some of the earliest Webb detections have already been re-evaluated. Objects that initially appeared to be at extreme redshifts have been reassigned to closer distances. Not all of them, but some. That's part of the process. Early data is noisy. Interpretations evolve. But here's the key detail. Even after revisions, the tension doesn't disappear. It narrows. It sharpens. It becomes more precise. Instead of a broad question, are these galaxies too early? It becomes a focused one. How early is too early? And that's where things get difficult, because there is no clean boundary, no single point where the model clearly fails. It's a gradient, a slow build-up of discrepancies, each one small on its own, but together significant. And this is where Webb's real power begins to show, because it's not just finding these objects, it's measuring them, breaking their light into spectra, analyzing the fingerprints of elements, determining star formation rates, estimating masses, and with each measurement, the picture becomes harder to simplify. Now, let's talk about what happens if these observations continue to hold, because that's where the implications start to spread outward. If galaxies are forming earlier than expected, then the timeline of the universe shifts, not dramatically in terms of total age, but in terms of structure formation, which means everything built on that timeline shifts too. Star formation histories, chemical evolution, the buildup of elements necessary for planets, the conditions required for life, all of it depends on when and how structures formed. And that means this is not just a question about distant galaxies. It's a question about the entire chain of events that eventually leads to us, because you live in a universe shaped by its earliest moments. The distribution of matter, the formation of galaxies, the creation of heavy elements, all of that traces back to the first few 100 million years. Change that, and you change the path. Now, this doesn't mean Earth wouldn't exist, or that life wouldn't emerge, but it means the story is different, and understanding that story matters, because it tells us how common or rare our kind of universe might be. If structure can form faster, then maybe galaxies like ours are more common, or maybe the opposite. Maybe we're seeing an unusual case, a region that evolved differently. That's still an open question, and it ties into something deeper, the idea of cosmic variance. The fact that the universe is not identical everywhere. On large scales, it's uniform, but on smaller scales, it varies. Clusters, voids, denser regions, sparse regions. And if Webb is observing a region with unusually early structure formation, it might not represent the whole universe. It might represent a local variation. But again, that explanation has limits, because as more regions are observed, the pattern persists, and the more it persists, the harder it is to attribute to chance. Now imagine what happens over the next few years. More deep field observations, more confirmed galaxies, better measurements, a growing data set. At some point, the data will become too strong to ignore, and that is when theory has to respond, not gradually, but decisively, because once you have a consistent pattern of early massive galaxies, you need a mechanism, a clear, testable explanation, and that explanation must fit everything else we know. That's the challenge, but it's also the opportunity, because this is how breakthroughs happen, not by design, but by friction between what we expect and what we observe. And right now, that friction is increasing, which brings us to what comes next. Because Webb is not alone. It's part of a larger ecosystem of observation. Other telescopes are already preparing to follow up. Ground-based observatories, spectroscopic surveys, future missions designed to map the early universe in even greater detail, each one adding another layer, another perspective, another test, and together they will either resolve this tension or deepen it. And if it deepens, then we are looking at something much larger than a simple adjustment. We are looking at a shift, not necessarily a revolution, but a change in how we understand the earliest phases of cosmic history. And those changes have a way of expanding. They expand outward, from one observation to a pattern, from a pattern to a pressure, from pressure to a shift in understanding that begins quietly, almost invisibly, before it becomes impossible to ignore. And if you've seen this before in science, it always follows the same arc. At first, the anomaly is small, contained, explainable. Then it repeats, in different datasets, under different conditions, and each time it does, it becomes harder to dismiss. Not because it's dramatic, But because it's consistent, that is where we are now, with the earliest light Webb is detecting. Consistency is starting to emerge. Not perfect, not complete, but enough to suggest that something deeper is happening. And this is where the story begins to open into something larger than galaxies. Because if the earliest structures in the universe form differently than we expected, then the entire architecture of the cosmos may have evolved differently, not radically, but subtly, in ways that accumulate over time. Think of it like changing the initial angle of a trajectory. A small difference at the beginning becomes a large difference later, and the universe has had 13.8 billion years for those differences to unfold. So, even a slight change in early structure formation could influence everything that comes after: the distribution of galaxies, the size of clusters, the formation of supermassive black holes, even the large-scale patterns we observe today. Now, this is where cosmology becomes something more than observation. It becomes reconstruction, because we are not watching the universe evolve in real time. We are piecing together its history from light that arrives at different moments, snapshots from different eras, and we arrange those snapshots into a timeline, a story. But what happens when some of those snapshots don't fit the sequence? You don't throw them away. You re-examine the sequence. You ask whether the order is correct, whether the spacing between events is accurate, whether something happened earlier than you thought. That is the process unfolding right now. And it is not just about Webb. It is about how Webb interacts with everything we already know. Because one of the strongest aspects of modern cosmology is that multiple independent observations agree. The cosmic microwave background, galaxy surveys, gravitational lensing, all of them point to a consistent picture, a universe that evolved in a specific way. So any new observation has to fit into that picture, or force it to change. And that's where the tension becomes real, because Webb's observations don't exist in isolation. They have to be reconciled with everything else, and that reconciliation is not simple. Now, let's take a step back, because it's easy to get lost in the details. What is actually at stake here? At its core, this is a question about time, about how long it takes for complexity to emerge. And that question appears everywhere, not just in cosmology, in biology, in geology, in any system where simple beginnings lead to complex outcomes. There is always a timeline, a sequence, arate, and when something appears earlier than expected, it forces you to reconsider the rate. Did things happen faster? Were the initial conditions different? Or are you missing part of the process? That is exactly the situation here. Because galaxies are complex systems, they are not just collections of stars. They are organized structures, with dynamics, with history, with internal processes that take time to develop. So when you see a galaxy that looks mature, at a time when it should still be forming, you are not just seeing an early object. You are seeing a compressed history, a sequence of events that seems to have unfolded more quickly than expected. And that is difficult to explain without changing something fundamental. Now, there is another layer to this, one that is less obvious, but just as important: observation limits. Because even with Webb, we are not seeing everything. We are seeing what we can detect, the brightest, the most massive, the most active. There could be countless smaller, fainter galaxies that we are missing. And if those exist, they might fill in the gaps. They might make the timeline smoother, more continuous. But even that doesn't fully resolve the issue, because the presence of smaller galaxies doesn't explain the existence of larger ones. It just adds context. So the question remains, how did the largest structures form so early? And this is where simulations become critical, because simulations allow scientists to test different scenarios, to adjust parameters, to see what happens when you change one aspect of the model. Right now, many of those simulations are being rerun, with updated inputs, with new constraints based on Webb's observations, and what they are finding is mixed. Some adjustments bring the model closer to the data, others don't. Some require extreme assumptions, conditions that may not be realistic. And that's the tension again. You can force a model to fit the data, but if the conditions required are too extreme, you have to ask whether you're still describing reality or just bending the model to match. And that is a line scientists are careful not to cross, because the goal is not to make the model fit. The goal is to understand what the universe is actually doing. And right now, the universe is telling us something, quietly, through light that has traveled for billions of years, arriving at a telescope positioned far from Earth, collected by mirrors that unfold in space, converted into data, analyzed, questioned, debated, and slowly understood, but not fully, not yet, and that not yet is where the most important part of this story lives, because there is a difference between not knowing and being close to knowing. And you can feel when science is in that second state, when the pieces are on the table, when the data is real, when the models are strained but not broken, when the answer is somewhere in reach, but still just out of alignment. That's where we are now, and the next few years will matter more than most people realize, because this is not a closed question, it's an active one. Right now, new observations are being scheduled, new deep field images are being captured, new spectroscopic measurements are being processed, and each one has the potential to either reinforce the pattern or reshape it. Now, imagine two possible futures. In one, many of these early galaxy candidates are revised downward, their distances adjusted, their masses reduced, their properties brought back into alignment with existing models. In that scenario, the tension fades, not completely, but enough to keep the current framework intact. It becomes a story of initial overestimation, of pushing instruments to their limits and refining interpretations over time. That has happened before, and it will happen again. But there is another possibility, one where more of these objects are confirmed, where additional observations reveal even earlier structures, where the pattern strengthens instead of dissolves. In that scenario, the pressure doesn't go away, it builds, and when pressure builds long enough in science, something shifts, not suddenly, but inevitably. Now, let's talk about what that shift might look like, because it's unlikely to be a single change. It won't be one discovery that flips everything. It will be a series of adjustments, some small, some larger, refinements to how we model early star formation, updates to how we simulate dark matter collapse, better understanding of how gas cools and fragments in the early universe, possibly even new physics, but only if the data demands it. Because science resists unnecessary complexity, it prefers the simplest explanation that fits all observations. So any major shift would need to be justified, supported, established. That's the standard, and Webb is helping define that standard by providing data that is precise enough to challenge assumptions, but also detailed enough to guide new models. Now, there is something else happening here, something less technical, but just as important: perspective. Because for a long time, the early universe felt distant, abstract, something described in equations and simulations. But now, we are seeing it, directly, not as a concept, but as light, actual photons that left their source billions of years ago, and are arriving now. That changes how we relate to it. It makes the early universe feel real, present, connected to us in a way that's hard to ignore. Because you are not just learning about something that happened long ago, you are receiving signals from it. Right now, that's what Webb is doing. It's not just looking into space, it's listening to the past, and the past is saying something unexpected. Now, let's step even further back, because this story is not just about galaxies, or dark matter, or cosmological models. It's about how we understand beginnings. The beginning of the universe is one of the most fundamental questions we can ask, not just scientifically, but philosophically. Where did everything come from? How did it evolve? Why does it look the way it does? And for a long time, we've had a model that answers those questions remarkably well. Not perfectly, but well enough to explain most of what we observe. and that model is still strong. That's important. Nothing we've discussed invalidates it, but it might not be complete, and completeness is what science is always chasing. Not perfection, but a closer approximation of reality. And sometimes, getting closer means discovering that what you thought was complete is missing something, not obvious, not dramatic, but significant, a piece that changes how everything fits together. And that's what these early galaxies might represent. Not a contradiction, but a clue, a sign that there is more to understand, more to uncover, more to refine. And that process is still unfolding. And as that process unfolds, something else begins to happen. The question itself evolves. At the beginning, it was simple. How can galaxies exist this early? But that question is already starting to split into more precise ones. How massive are they really? How quickly can gas collapse under early conditions? What role did the first stars actually play? How uniform was the early universe? Each of these questions branches into others, and each branch leads deeper into the same territory, the place where observation meets theory, where numbers meet interpretation, where data forces clarity, because there is a limit to how long you can hold tension in a model. Eventually, it resolves, one way or another. Now, to understand where this is heading, you have to understand how scientific resolution actually works. It doesn't arrive as certainty, it arrives as convergence. Multiple lines of evidence pointing in the same direction, independent measurements agreeing, different methods producing consistent results. That's when confidence builds. That's when models stabilize. And right now, we are not there yet, but we are moving toward it, because Webb is not just finding galaxies. It is characterizing them, measuring their light in detail, breaking it into spectra, looking for signatures of hydrogen, oxygen, carbon, tracing star formation rates, estimating ages. And as more of these measurements come in, the uncertainties shrink, the picture sharpens, and the room for interpretation narrows. That's when the real answers begin to emerge. But until then, we are in a phase of exploration, and exploration always feels unstable, because you are moving through unknown territory, mapping it as you go. Now, let's return to something we touched on earlier. Reionization, because this is where many of these observations converge. The early universe wasn't just dark, it was neutral, filled with hydrogen atoms that absorbed light. For the universe to become transparent, those atoms had to be ionized, stripped of their electrons, and that required energy, a lot of energy. The standard explanation is that the first stars and galaxies provided it, slowly, over hundreds of millions of years. But if galaxies formed earlier and were brighter than expected, then they could have contributed to reionization sooner, or more efficiently, or unevenly. Think of it like turning on lights in a dark city. If a few buildings light up early, the darkness doesn't disappear all at once. It recedes in patches. Some areas become visible before others. And that might be what happened. A patchy reionization, regions lighting up earlier than expected, driven by early, luminous galaxies. If that's true, then Webb isn't just detecting anomalies. It's revealing how the universe transitioned from darkness to light in a way we didn't fully anticipate, and that connects directly to what we see today. Because the transparency of the universe affects everything. How light travels, how we observe distant objects, how structures evolve. So understanding reionization is not optional, it's central, and Webb is giving us new clues about how it unfolded. But those clues come with the same tension, because if reionization happened earlier, or differently, then the sources driving it must have existed earlier too. And that brings us back to the same question. What formed those sources? What allowed them to exist so soon? Now, there is another possibility that has been discussed, one that is less about changing the model and more about changing our interpretation. What if we are overestimating the masses of these galaxies? Because mass is not measured directly, it's inferred from brightness, from spectra, from models of stellar populations. And if those models are slightly off, if early stars behave differently than we assume, then our estimates could be skewed. For example, if early stars were more efficient at producing light, then a galaxy could appear more massive than it actually is. Think of it like judging the size of a city by how bright it looks at night. If the lights are unusually intense, you might assume the city is larger than it really is. That's a real possibility, and it's being tested. But again, it has limits, because brightness alone doesn't explain structure, or chemical signatures, or the distribution of light within these galaxies. Those features still point to complexity, and complexity still requires time, which brings us back, again, to the same unresolved tension. And at this point, you can start to see the pattern. Every explanation addresses part of the problem, but none of them fully resolve it. Not yet. And that's why this is still open, still active, still being worked through, because the universe is not giving us a simple answer. It's giving us data and asking us to interpret it. And interpretation is where everything becomes fragile, because data doesn't speak on its own. It has to be translated, converted from photons into numbers, from numbers into models, from models into meaning. And at every step in that chain, assumptions are involved. Careful ones, tested ones, but still assumptions. So when something doesn't fit, you don't just question the observation, you question the translation. Where did we interpret something incorrectly? Where did we assume something that might not hold under these conditions? And in the case of the earliest galaxies, there are several points where that translation could be shifting. One of them is stellar populations. The stars inside these early galaxies are not like the stars you see in the night sky today. They formed under very different conditions. Lower metallicity, different gas composition, different cooling processes, which means their light behaves differently. Their spectra look different. Their brightness evolves differently over time. And if our models of those early stars are incomplete, then everything we infer from their light could be slightly off. Mass estimates, age estimates, star formation rates, all of it. Think of it like trying to estimate the age of a tree, using rules developed for a completely different species. You might get close, but small differences can lead to large errors over time. That's one area under intense study right now, refining stellar population models for the early universe. Because if we can better understand how those stars behave, we can better interpret what Webb is seeing. Another area is dust. Interstellar dust plays a huge role in how light is absorbed and re-emitted. And in the early universe, dust may have formed differently, faster in some cases, more abundantly in others. If early galaxies contain more dust than expected, it could affect how we interpret their brightness and spectra, making them appear older or more massive than they are. But again, there are limits. Dust can obscure, it can redden light, but it doesn't create structure, it doesn't generate the underlying complexity we're observing. So while it's part of the picture, it's not the whole explanation. And then there's something else, something more subtle, selection effects. We touched on this before, but it's worth going deeper, because telescopes don't see everything. They see what they are sensitive to, what stands out, what crosses the detection threshold, and that means we are biased towards certain types of objects. The brightest, the most active, the easiest to detect. So when Webb looks deep into the universe, it's not giving us a complete census. It's giving us a filtered view, a highlight reel, and that can distort perception. If you only see the largest galaxies, it might look like all galaxies formed early, when in reality, you're just seeing the extreme cases. Think of it like looking at a city from a distance at night. You see the skyscrapers first, the brightest lights, the most prominent structures, but that doesn't mean smaller buildings don't exist. You just don't see them yet. That's a real effect, and it's being accounted for. But even with that in mind, the existence of these large, early galaxies still requires explanation, because even rare objects have to form somehow, and that somehow is what's under investigation. Now, here's where the story begins to turn towards something more fundamental, because everything we've discussed so far lies within the framework of known physics: gravity, dark matter, gas, dynamics, star formation, all understood, at least in principle. But what if the solution doesn't sit entirely within that framework? What if there is something about the early universe that we haven't fully captured yet? Not because it's hidden, but because we haven't had the data to reveal it. This is where the idea of new physics enters the conversation. Carefully, cautiously, because proposing new physics is not taken lightly. It's a last resort, used only when existing models cannot accommodate the observations. And we are not there yet, but we are approaching a boundary where that possibility has to be considered, not as a conclusion, but as a question. What if something about the early universe behaved differently? What if there were processes active then that are no longer present now? Transient phases, short-lived conditions, that accelerated structure formation, that allowed matter to organize more quickly, and then faded, leaving behind a universe that follows the rules we observe today. It's not a wild idea. The universe has gone through multiple phases: inflation, recombination, reionization, each one with different conditions, different dynamics. So it's possible that there was another phase, one we haven't fully understood yet. And if that phase affected how galaxies formed, it could explain what Webb is seeing. But again, this is not proven. It's being explored, tested, modeled, compared against data, because that's the process. You don't jump to conclusions. You build them, step by step, from evidence. And right now, the evidence is still being gathered. And as that evidence builds, something subtle begins to happen inside the field. The language changes. At first, everything is framed as an anomaly, a curiosity, a deviation that needs explanation. But over time, if the anomaly persists, it stops being treated as an exception. It becomes part of the data, and once something becomes part of the data, the model has to include it. That transition is not announced. It doesn't happen in a single paper. It happens gradually, across dozens of studies, across different teams, until one day, what was once considered unexpected is simply accepted as something the universe does. We are not there yet, but we are moving in that direction. Because the number of early galaxy candidates is growing, the quality of observations is improving, and the explanations are being refined. Now, let's focus on something specific. The term that has started to circulate in discussions about these observations: impossible galaxie. It's not an official classification. It's not a formal category, but it captures the feeling. Galaxies that, under standard assumptions, should not exist at the times we are seeing them. And that label is telling, because it reflects a tension between expectation and observation, not a contradiction of physics, but a mismatch in timing. And timing is everything in cosmology, because time determines what processes are possible, what structures can form, what histories can unfold. So when timing is off, everything shifts. Now, one of the most important aspects of this situation is that it's not binary. It's not that galaxies either should or shouldn't exist. It's about how many, how massive, how evolved, and that nuance matters, because the universe is not uniform. It's statistical, probabilistic. There will always be outliers, objects that form earlier than average, regions that evolve faster. But those outliers have limits. They exist within a distribution, and what Webb is showing us may be pushing the edges of that distribution, or extending it. And that distinction is critical, because if we are just seeing the extreme end of a distribution, then the model holds. It just needs to account for those extremes. But if the distribution itself is different, if early structure formation is more common than expected, then the model needs to change. And that's what scientists are trying to determine. Where does the distribution actually lie? And Webb is giving us the data to answer that. Now, Let's shift perspective for a moment, because everything we've discussed so far has been from the outside looking in, observing distant galaxies, interpreting their light. But there is another way to think about this. From the inside out, you live inside a galaxy, the Milky Way, a structure that took billions of years to form, with hundreds of billions of stars, complex dynamics, a long history of mergers and evolution. Now imagine looking at your own galaxy at an age of only a few 100 million years. What would it look like? It wouldn't look like this. It would be smaller, less organized, less chemically enriched, still forming, still evolving, and yet some of the galaxies Webb is observing at that age already show signs of advanced structure, not identical to the Milky Way, but further along than expected. And that comparison is important because it anchors the scale of the discrepancy. It's not abstract, it's relative to something we understand. Now, this brings us to something deeper, the nature of cosmic time itself, because when we talk about early and late, we're using human language to describe something that operates on scales far beyond human experience. Hundreds of millions of years, billions of years, these are not intuitive. So we rely on models, on sequences, on expectations. But those expectations are only as good as the assumptions behind them. And Webb is testing those assumptions directly by showing us what existed at specific points in time. Now, here's a question that doesn't have a simple answer. What if the universe is more efficient at creating complexity than we thought? What if, under the right conditions, structure emerges faster, more rapidly, more dynamically than our models predict? Because complexity is not just about time, it's about conditions, energy, density, interactions, and the early universe had conditions we can't fully replicate. Extreme temperatures, high densities, rapid expansion, all interacting in ways that are difficult to simulate perfectly. So it's possible that our models are missing something about how those conditions translate into structure, not because the physics is wrong, but because the interactions are more complex than we've captured. And that's a subtle but important distinction, because it means the answer might not require new physics. It might require better understanding of existing physics, at scales and conditions we haven't fully explored. And that is often how progress happens, not by replacing what we know, but by refining it, extending it, making it more accurate. But again, that's not confirmed. It's a possibility, one of several, and the only way to test it is with more data, more observations, more analysis, which brings us back to where we are, right now. Right now, the telescope is still watching. It hasn't stopped. It doesn't pause between discoveries. Every time it locks onto a new patch of sky, it is collecting photons that have been traveling since before the Earth existed. And every one of those photons carries the same question. What was already there? Not what could have been there. Not what should have been there. What was actually there? Because that distinction is everything. The universe doesn't care about our expectations. It doesn't follow our models. It simply does what it does, and we try to catch up. Now imagine this from Webb's perspective. It stares into what looks like emptiness, a black patch of sky with no visible structure, and over hours, days, sometimes weeks, light begins to accumulate, faint signals, barely above the noise. And then, slowly, a shape emerges. A point of light becomes a galaxy. A blur becomes structure. A signal becomes data. And when that data is processed, it reveals something that has been there all along, hidden, not because it was invisible, but because we didn't have the tools to see it. That's the power of Webb. It's not creating anything new. It's revealing what already exists. And what it's revealing is forcing us to rethink the earliest chapters of the universe. Now, there's something almost unsettling about that, because for decades we believed we had a relatively clear picture of how the universe evolved. Not perfect, but consistent. The timeline made sense. The sequence of events was coherent. And now, that sequence is being questioned. Not entirely, but enough to matter. Enough to introduce uncertainty. And uncertainty is where understanding begins to deepen. Because when something doesn't fit, you have to look closer. You have to ask better questions. You have to test assumptions that you once took for granted. And that's exactly what's happening. Now, let's move toward the edge of this story, because everything we've talked about leads to a single, unresolved point, a question that sits at the center of all of this. If these galaxies truly formed earlier than expected, what does that say about the beginning itself? Not just the formation of stars, but the conditions that made star formation possible, because the earliest moments of the universe set the stage for everything that followed. The distribution of matter, the energy landscape, the initial fluctuations, all of it originates there. So if something is off later, it might trace back to something earlier, something subtle, something we haven't fully captured yet. And that brings us to a place where science becomes almost philosophical, because we are asking about origins, about how something complex emerges from something simple, about how structure arises from chaos. And those questions don't just belong to cosmology, they belong to everything. Now, here is where the story refuses to resolve, because we don't have the final answer. Not yet. We have observations, we have models, we have hypotheses, but we don't have a complete explanation. And that's not a failure. It's the current state of knowledge, a snapshot in time, just like the light Webb is collecting, a moment in the process of understanding. And that process is still moving, still evolving, still being shaped by new data. Now, imagine looking at the universe from far enough away, not from Earth, not from within the Milky Way, but from a vantage point where you can see everything at once. The entire history, the entire structure, all at once. From that perspective, there is no mystery. Everything simply is. But from where we are, inside it, looking outward, we see fragments. We piece them together. We build models. We refine them. And occasionally, we find something that doesn't fit. Something that forces us to reconsider. That's what this is. A moment where the universe is showing us something unexpected. Not impossible, not contradictory, but incomplete. And that incompleteness is the most important part, because it means there is more to learn, more to uncover, more to understand. Now, let's return to the beginning. Right now, light is reaching Earth that should not exist. Not because it's breaking the laws of physics, but because it doesn't fit the story we told about how the universe began. And that story is still being written. Every observation, every measurement, every new piece of data adds to it, changes it, refines it, and sometimes forces us to rewrite parts of it entirely. The James Webb Space Telescope is not the end of that story. It's the beginning of a new chapter, one where we are no longer guessing what the early universe looked like. We are seeing it directly, and what we are seeing is raising questions we didn't expect to ask. Now, here is the part that stays with you. You are standing on a planet, orbiting a star in a galaxy that formed billions of years after the events we're talking about. Everything you know, everything that exists around you, is the result of processes that began in those first few 100 million years. And right now, we are realizing that those processes may not have unfolded the way we thought, which means the path from the beginning to this moment may be different than we imagined. Not completely different, but enough to matter, enough to change how we understand our place in it. And the question that remains, the one that doesn't have an answer yet, is this: if the universe could build something complex faster than we thought, what else about it have we underestimated? Because whatever that answer is, it's already out there, its light is already on the way, and we're only just beginning to see it.